All right, welcome everyone to the next New York Combinatorics seminar. Today we're happy to have Cece Henderson from Waterloo, who's going to talk about hypergraph Nash-Williams conjecture. Take it away.
Perfect. Thank you so much for having me. I'm really excited to be here. Everything I'm talking about today is joint work with Michelle Delcourt, Thomas Lesgourgues, and Luke Postle. Okay, so we're going to start off with some background information about the existence of designs. Now, questions about combinatorial designs are some of the oldest in combinatorics. So, for example, here's a question from the Ladies and Gentlemen's Diary of 1846 that Kirkman asked. So he was asking, how many triads can be made out of n symbols so that no pair of symbols shall be comprised more than once amongst them? So, or maybe in some more modern language, if we have n symbols, we want to group them in groups of three so that no pair of symbols is together more than once. And in particular, Kirkman explored the case where each pair appears in exactly one of these triples. Now, there are a couple necessary divisibility conditions for Kirkman's question. So in particular, the number of pairs needs to be divisible by 3, and the number of pairs containing each element also needs to be even. And so you can work through that algebra and get that n has to be equivalent to 1 or 3 mod 6. So then Kirkman's question becomes, when is this necessary condition sufficient? And it turns out that it always is. So Kirkman showed in 1847 that it's possible to find a set of triples of a ground set of size n such that every pair of elements appears in exactly one triple if and only if n is equivalent to 1 or 3 mod 6. And such a set of triples is called a Steiner triple system. There's a bit of a misnomer there, but that's a story for another day. Now, the most famous example of a Steiner triple system, the one you're most likely to have seen before, is called the phonoplane. So here we have a ground set of size 7, which I've labeled A on. And on the left, you can see this sort of set theory notation. We have sets of 3, but often this is visualized as this triangle diagram over here. So every line represents a triple. So we have the red ABC, and here we have the red line ABC. And you can see that every pair of these nodes is together in exactly one line. So it's a Steiner triple system. Now, there's a couple easy ways to think about generalizing Kirkman's question, right? He was asking about every pair of elements, thinking about placing them in triples, right? There's some fertile ground here for generalization. So in particular, an NQR Steiner system is a set S of Q subsets of an N set X, such that every R subset of X is contained in exactly one element of S. So if you work through this definition, a perfect matching is an N21 Steiner system, and then a Steiner triple system is an N32 Steiner system. Now, I don't know about you, but the very first time looking at this definition, especially if it's your first time, it's been on the screen for 30 seconds. It's a lot of parameters to work through and wrap your head around really quickly. So let's see if we can instead try to visualize what this is really saying. So we're talking about a ground set of size n. Okay, great. Put n vertices. And we have this condition about the R subsets of this ground set. Now, for the purposes of visualization, I'm going to pick R equals 2. It's just going to be easier to draw. And we have a condition on every R subset. So I'm going to draw every possible 2 subset of my ground set, right? Where most of us are combinatorialists here, this is starting to look pretty familiar as a complete graph. And then we want to divide these R subsets, these edges, into Q subsets. So if Q equals 3, right, the parameters of this Steiner triple system, what we're talking about is trying to find these edge disjoint triangles in a complete graph. And suddenly, at least for me, this made the definition really click. And now we have something a lot more familiar if you do graph theory. So in particular, given hypergraphs F and G, an F decomposition of G is a partition of the edges of G into edge disjoint copies of F. And we're going to use this K sub n to the R to denote the complete R uniform hypergraph on n vertices. So then, as we just saw on the following slide, or on the previous slide, an NQR Steiner system is equivalent to a KQR decomposition of KNR. So returning to our phonoplane example, right, we had the set theory visualization on the left, the classic triangle diagram in the middle, but now we could represent this as a triangle decomposition of K7. So again, we had this red set ABC, which corresponded to the line ABC in the middle, which is now this triangle ABC on the right. And we know that this is a Steiner triple system because every edge in this complete graph is contained in exactly one triangle. Now, just as with Steiner triple systems, there are some necessary divisibility conditions if we want to have a hope for a graph containing an F decomposition. And in particular, we say that a hypergraph G is F divisible if it meets those necessary divisibility requirements for an F decomposition. The nitty-gritty decomposition requirements change depending on exactly what question you're asking. So going forward, we'll just say F divisible. And now a classic conjecture from the mid-1800s, a classical conjecture, was, well, again, when are these necessary conditions sufficient? So the existence conjecture from the mid-1800s posited that they always are. So in particular, it posited that if n is sufficiently large and KNR is KQR divisible, then KNR always admits a KQR decomposition. Or equivalently, the necessary conditions are sufficient for the existence of these NQR Steiner systems. So in some sense, the Steiner triple system, Kirkman's results on Steiner triple systems, isn't special to triangles. Really, this should be true for any choice of parameters. Now, even though this appears in the literature starting in the mid-1800s, so it's been around for a long time, it wasn't until the past decade or so that we got any proofs of the existence conjecture. So in particular, Keevash first provided the first proof of this result in 2014 using randomized algebraic constructions. Shortly after, Glock, Kühn, Low, and Osthus proved it as well using a different method called refined absorption. And recently in 2024, Delcourt and Postle provided a proof using a methodology that they call refined absorption, which is sort of the framework that we use for our results that I'll talk about later in this talk. So keep that in mind. And again, Keevash provided an even shorter proof following this framework also in 2024. So now a wealth of proofs of the existence conjecture. And that brings us to part 2, the Nash-Williams conjecture. So with the resolution of the existence conjecture, we know that complete hypergraphs, always decompose into smaller complete hypergraphs. Well, this begs the question, what about decompositions in non-complete graphs? And unfortunately, it's not quite as simple anymore, because when G is not complete, divisibility is no longer enough. So in particular, a graph is K3 divisible if every vertex has even degree and the number of edges is divisible by 3. Well, let's take a look at C6. C6 does meet this definition. It is K3 divisible, but the cycle on 6 vertices does not even contain a triangle as a subgraph, so there's absolutely no hope that it's K3 decomposable. Okay, so we need another condition, right, for this question about decompositions in non-complete graphs. And intuitively, the higher the minimum degree, this delta of G, well, then the closer our graph is to being complete and hence addressed by the existence conjecture. So then a natural question is a high minimum degree in a divisible graph enough to guarantee the existence of a decomposition? And the Nash-Williams conjecture of 1970 addresses the triangle case of this question. So it posits that if G is a sufficiently large K3 divisible graph with minimum degree at least 3/4 times the number of vertices, then G admits a K3 decomposition. And in 1970, Graham showed that this constant 3/4 would be tight if it's true. Now, I want to take a few minutes and talk about the significance, or what I perceive as the significance of this conjecture. So first, I would argue that this conjecture really is central to extremal combinatorics. So recall, maybe if you ever had the chance to be in a combinatorics class, maybe from your introductory class, there are some really heavy-hitting results here. So first of all, there's Mantel's theorem, which gives us a lower bound on the number of edges needed to guarantee the existence of a K3 subgraph. And this Mantel's theorem is sort of the base case for Turán's theorem, which sparked the whole subfield of Turán theory, which is truly at the heart of extremal combinatorics. Well, then the 1963 result from Corradi and Heinel gives a minimum degree threshold, a tight minimum degree threshold for the existence of a K3 factor. And so Nash-Williams conjecture extends this deeply rooted lineage, right, from the existence of a K3 subgraph with Mantel's theorem and more broadly Turán's theorem to the existence of a K3 factor, where we're taking vertex disjoint spanning copies of triangles from the Corradi-Heinel theorem, which again is the base case of the hard-hitting results, Heinel-Semiretti's theorem. Well, then Nash-Williams conjecture extends this to the existence of a triangle decomposition. So now edge disjoint spanning copies of triangles. The Nash-Williams conjecture is also relevant to a classical design theory completion problem. If it's true, then any partial K3 decomposition of a divisible Kn with maximum degree at most 1/4 n is completable to a full decomposition or a full design. So that's powerful in and of itself. And finally, the Nash-Williams conjecture also generalizes Dirac's theorem, which is also another really heavy-hitting result in combinatorics. So recall that Dirac's theorem from 1952 says that if we have enough vertices and minimum degree at least 1/2 times our number of vertices, then G is Hamiltonian. In other words, if our number of vertices is even, this implies that G has a perfect matching. And a perfect matching is an n-to-1 Steiner system, so the Nash-Williams conjecture generalizes this notion to an n-3-2 Steiner system. So if you take nothing else away from this talk today, other than the significance of the Nash-Williams conjecture, well, I would be happy. Now, in terms of progress on the Nash-Williams conjecture, the best known progress was obtained by what we'll call tying the K3 decomposition threshold to the fractional K3 decomposition threshold. So a fractional F decomposition is a collection of F subgraphs of G, each with a weight between 0 and 1, such that the total weight on each edge of G over all copies of F containing that edge is exactly 1. And fractional decomposability is necessary for decomposability because an F decomposition is a fractional F decomposition, just where all the weights are exactly 1. And then the fractional F decomposition threshold, which will denote delta star sub F, is the infimum of all these constants greater than 0, such that every graph with minimum degree at least that constant times the number of vertices has a fractional F decomposition. So the best known result for the Nash-Williams conjecture is that minimum degree at least sort of this fraction here times the number of vertices guarantees that a K3 divisible graph has a K3 decomposition. And if you put this into a calculator, you'll get that this number is approximately 0.83. And this is obtained through the combination of two different results. So first, in 2016, Barber, Kühn, Lowe, and Osthus showed that for every epsilon, any sufficiently large K3 divisible graph G on n vertices with minimum degree at least the fractional threshold admits a K3 decomposition. So in particular, this implies that showing that the fractional decomposition threshold is at most 3/4 would prove the Nash-Williams conjecture asymptotically. So this is what I mean by tying the decomposition threshold to the fractional decomposition threshold. And then in 2021, Delcourt and Postle improved the bound on this fractional threshold to at most the constant seen here. Okay. Given all that, it's time to talk about how we generalize the Nash-Williams conjecture. First, to KQ decompositions. So recall, here's the Nash-Williams conjecture at the top, and here's a folklore generalization of the Nash-Williams conjecture for KQ decompositions. It states that for every Q at least 4, if G is a sufficiently large KQ divisible graph with minimum degree at least 1 minus 1 over Q plus 1 times the number of vertices, then G admits a KQ decomposition. Right, and this generalizes the Nash-Williams conjecture because if we plugged in Q at least, or if we plugged in Q equals 3, we would get that 3/4 number. And a construction from Gustafsson in 1991 shows that this minimum degree threshold would be tight. So once again, we have some similar work on this more general folklore conjecture. In 2016, Glock, Kühn, Lowe, Montgomery, and Osthus tied the KQ decomposition threshold to the fractional KQ decomposition threshold for all Q at least 3, right? And in 2019, Montgomery gave a bound on this fractional threshold and showed that it was at most 1 minus 1 over 100 Q. So not quite Q plus 1, but it seems like the beginning of getting the ball rolling to maybe show some incremental progress to hopefully finally prove this result, just like with the Nash-Williams conjecture. Unfortunately, in 2025, we showed that actually the folklore generalization of the Nash-Williams conjecture is false. And in fact, even the fractional relaxation of the folklore generalization of Nash-Williams is false. We showed that for each Q at least 4, the fractional threshold is strictly greater than 1 minus 1 over Q plus 1. And even worse, the folklore generalization is even off by a multiplicative factor. So for every epsilon greater than 0 and every large enough Q in terms of epsilon, you can get that the fractional threshold is strictly greater than 1 minus 1 over this constant term times Q plus 1. And where that constant is strictly greater than 1. Now, I'll talk briefly about the construction for a counterexample that we found. And using independent blowups, it suffices to find one counterexample. It turns out if you can find one counterexample for each Q, then there's an easy process to blow up that counterexample and get infinitely many. in terms of the number of vertices, therefore disproving the conjecture. And the join of graphs H1 through HK is obtained by making each HI pairwise complete to each other. So then a counterexample for Q equals 7 is just the join of 5 C5s. Why? It's a space barrier. There's just simply too many cross edges between these C5s to cover, given the number of internal edges. There's just not enough space for a decomposition. But if you do it out, it does meet the minimum degree threshold proposed by the general conjecture. And I'll spare you the details of the calculation and our general construction, but we generalize this for all Q at least 4. However, though, our construction, nothing we could do worked for the Nash-Williams conjecture. So the Nash-Williams conjecture lives on as potentially being true, but not the folklore generalization. Okay, well, we can't end on a negative note, a disproof. So instead, let's talk about generalizing the Nash-Williams conjecture in a different direction to hypergraphs. So an R graph is an R uniform hypergraph. So every edge has R vertices. And if G is an R graph, we use delta sub R minus 1 of G to denote the minimum number of edges containing any set of R minus 1 vertices in G. This is one natural way to generalize what minimum degree means in hypergraphs. And if I made a type, I try to catch myself, but sometimes I'll just use delta of G, our normal minimum degree notation. And when I'm talking about an R uniform hypergraph, what I mean is this R minus 1 degree. Okay, well, in 2021, Glock, Kühn, and Osthus proposed a hypergraph Nash-Williams conjecture. They posited that for fixed positive integers, Q and R, if G is a sufficiently large KQR divisible R graph with minimum R minus 1 degree, at least this number times the number of vertices, then G has a KQR decomposition. In terms of progress on this conjecture, Glock, Kühn, and Osthus showed in 2023 that there exists infinitely many KQR-free R graphs G with minimum degree, at least this number, where their bound is derived from Turán theory, right? Turán theory says what's sort of your minimum density that you need to guarantee the existence of a copy of KQR. And well, we certainly need one copy of KQR if we're going to find a decomposition. And in 2023, Glock, Kühn, and Osthus also showed that for all R less than Q, all sufficiently large divisible R graphs with minimum R minus 1 degree, at most this number, admit a KQR decomposition. And I'll highlight that there's like quite a big gap between these two bounds, right? Between the upper and the lower bound. So there was a lot of fertile ground to play with here. So then Luke and my main theorem is progress towards this conjecture. We tied the KQR decomposition threshold to the fractional KQR decomposition threshold. More specifically, we showed that for every Q at least R greater than or equal to 3 and positive epsilon, every sufficiently large KQR divisible R graph with minimum degree, the maximum of the fractional threshold plus epsilon and the proposed bound times the number of vertices admits a KQR decomposition. And in 2025, Delcourt, Lesgourgues, and Postle also showed that they gave an upper bound on this fractional threshold. And so combining these two results, we get the following corollary, which is that for every integer q at least r and real epsilon at least 0, every sufficiently large KQR divisible R graph G with minimum degree at least 1 minus something almost on the order of what's conjectured, right? We just have this little epsilon here, but getting pretty close to the conjectured bound, times the number of vertices admits a KQR decomposition. With my remaining time, I'll give you a high-level proof overview of how we showed this result. So we use the absorption method, which is a method for turning almost decompositions into complete decompositions by beforehand setting aside a structure which we call an absorber capable of decomposing the possible leftover. So I like to think of the absorption method as having a little bit of foresight. First, you preserve this special graph, then finding an almost decomposition in general is much easier than finding a complete decomposition. And then you let the absorber do the work to take that almost decomposition into a complete decomposition. More formally, a KQR absorber for a KQR divisible subgraph L is a subgraph A such that, first of all, the vertices of L are independent in A. And both A union L and A are KQR decomposable. So this is almost like a light switch, right? If in our almost decomposition, L is left out of the almost decomposition, well, that's totally fine. We can take the union of A and L and decompose those together. Excellent. But if instead L is included in the almost decomposition, well, that's totally fine too. A is capable of decomposing itself. Now, when you first see this definition, it seems a little magical, right? A little too convenient. But in fact, in 2016 and recently published in 2023, Glock, Kühn, and Osthus showed that if L is a KQR divisible hypergraph, then indeed there does exist a KQR absorber A for L. So these structures do exist. Excellent. Now, to use absorbers to find a decomposition, though, we have to have one for any possible leftover of the almost decomposition, right? We sort of have to know what the possible leftovers are and ahead of time reserve an absorber for each of them, which is a lot. That means reserving a lot of individual absorbers, which has proven to be a barrier for some methods or for some proofs that use the absorption technique. So this motivates the following stronger definition. An R graph A is a KQR omni-absorber for an R graph F if the vertex sets are equal and A and X are edge disjoint. So that's analogous to the vertex set of L being independent in A. Fine. And here's where it's stronger. For every KQR divisible subgraph of X, there exists a KQR decomposition of A union L. So A is really powerful in that no matter what part of L is left in X, as long as it's KQR divisible, A says, don't worry about it, I got it. I can decompose this and turn the almost decomposition into a complete decomposition. Once again, I think this definition is a little bit magical. At least when I first saw it, I was like, well, sure, that would be convenient, but how do we know such an omni-absorber exists? Now, it's actually the existence of omni-absorbers is not too hard, right? You could just take the union of absorbers for every possible KQR divisible subgraph of L. But again, we run into the same problem of that's a lot. That's a really sort of big subgraph. So instead, we really want to think about, do there exist efficient KQR omniabsorbers? Small, low max degree. Yeah, so as I said, the union of all possible omniabsorbers is an omniabsorber, but the size of such a construction makes its use infeasible. But in 2024, Delcourt and Postle proved the existence of linearly efficient KQR omniabsorbers in dense enough settings. Bingo, there we go. That's what we're looking for. And this is sort of a key theorem in their proof, in their one-step combinatorial proof of the existence conjecture. So as a reminder, here's the existence conjecture from the mid-1800s. It posited that if n is sufficiently large and KNR is KQR divisible, then KNR admits a KQR decomposition. Here's a brief proof outline of Delcourt and Postle's 2024 existence conjecture proof. So first, they randomly reserve a small set of edges X of KNR. Using the Chernoff bound, not super hard. Then they use the theorem we just talked about on the previous slide to reserve an efficient omniabsorber A for X. And their theorem functions as a black box, these existence of omniabsorbers in dense enough settings. Wonderful. Next, they regularity boost what's left in the clique besides what we've already reserved. We've reserved X and we've reserved A. So we regularity boost what's left to find a very regular set of cliques. And that's because in the next step, we apply nibble with reserves, this sort of algorithmic result that allows you to find a partial decomposition. And nibble runs best with when you input very regular sets of cliques. So that's why we needed step 3. But then yeah, our last step, apply nibble with reserves to find a partial KQR decomposition Q of KNR minus the omniabsorber. We don't want to touch that. Covering all edges of the clique that aren't in X or A. So if we put this together, then what's left over from this partial decomposition? Well, it can only live in X, right? Nibble with reserves said that we pushed our leftover into this special set X. Great. Well, by definition of the omniabsorber, A is capable of decomposing what's left. And so that gives us another KQR decomposition just of this leftover in A called Q prime. And then Q union Q prime is the desired KQR decomposition of KNR. I like this proof because even though it relies definitely on having some knowledge of the notation and what all of these things mean, when you boil it down to it, it really is an elegant 4-step proof of this conjecture that was open for a couple hundred years. Okay, well, how can we adapt this refined absorption framework from the last slide to the hypergraph Nash-Williams setting to prove the following result? So just as a reminder, this is the main theorem that Luke and I proved. Well, step 1, we're still going to randomly reserve a small set of edges X, but this time we're reserving them in our graph G instead of in the complete graph. That's not too hard. Chernoff bounds will still do that for you. Step 2 is to reserve an efficient omniabsorber A for X in G. Now, this actually is the main obstacle of our proof because Delcourt and Postle's black box says that these omniabsorbers, they exist, but in dense enough settings, in quite dense settings. And our graph has high minimum degree, but it's not nearly dense enough to just automatically guarantee the existence of an omniabsorber. Okay, so that's an obstacle. But then step 3, we regularity boost what's left in G instead of in the complete graph. And this step is non-trivial, but given our previous work, we were able to adapt some of our lemmas to this setting quite nicely. And then finally, once again, apply nibble with reserves, again, to G. And nibble has been adapted to this before, so that step is also not bad. So for the remainder of this talk, we'll really be talking about how to accomplish step 2. How do we find this omni-absorber A for X in our high minimum degree graph G? Okay, so Nash-Williams omni-absorbers. The idea is still going to be to use Delcourt and Postle's refined efficient omni-absorber theorem as a black box in our hypergraph Nash-Williams setting. But as we talked about, that guaranteed omni-absorber, it might use edges in the complete graph, KNR, that are not present in our graph G. So then our solution is going to be to embed small subgraphs or small gadgets into G. So in particular, for every edge of this initial omni-absorber, we're first going to embed what we call a fake edge. It's a subgraph or a gadget in G that has the same divisibility properties of an edge. And so those, we're going to find them in G using the edges we actually have. Then, for every clique that the initial omni-absorber A0 wants to use, right? It really wants to use this clique to decompose a leftover. Well, we embed a private absorber for the associated collection of fake edges. So if the omni-absorber wants to use this clique, instead we say, no, sorry, you have to use these fake edges that are now actually legitimately in G. But the fake edges, well, they might no longer have this lovely property of the omni-absorber where they have a decomposition. We just know that they have the same divisibility properties, so they are decomposable. And that's where, on top of those, we embed private absorbers to handle the fake edges. Okay, that was a lot of detail, but at a high level, really to solve this Nash-Williams omni-absorber problem, it's an embedding problem. And by the general embedding lemma, which we cooked up in 2025, it is sufficient to show there exists enough, aka a constant proportion of all the possible, embeddings of each gadget into G. So if nothing about the fake edges or private absorbers made sense, really what we're doing at a high level is we just want to show that if we have a small subgraph that I want to embed, I have enough possible options for where to put that subgraph in G. And if that's true for every single thing we want to embed, then by this general embedding lemma, we're done. We've accomplished step 2 of the proof. Well, how do you do that? How do you show that there's enough ways to embed sort of a rooted subgraph into the base graph G? The classic solution to this that appears often in the literature is to use rooted degeneracy. So a hypergraph H has rooted degeneracy D if there exists an ordering of the non-root vertices with at most D earlier neighbors. And then it's not too bad to show that if your graph has minimum degree at least 1 minus 1 over D plus epsilon times the number of vertices, and H has rooted degeneracy at most D, then there exist enough embeddings of H into G. And you do that by arguing that you can embed H one vertex at a time in this rooted degeneracy ordering. And in fact, the strategy works to embed fake edges, the first type of gadget we wanted to embed. Fake edges have rooted degeneracy at most Q minus 1, choose R minus 1. That works with the minimum degree condition we have. Excellent, we're done. What about embedding private KQR absorbers. That was the second category of gadgets we wanted to embed. And for that, we're going to need to look at what KQR absorbers look like in the hypergraph setting. KQR absorbers, at least the construction that we use, are built from two other constructions. First is a KQR booster, which is a non-trivial absorber for a copy of KQR. This, at a high level, just allows us to avoid using a specific clique in a decomposition. And for two cliques, S1 and S2 overlapping on an edge E, H is a KQR hinge if H union S1 minus the edge admits a KQR decomposition, and H union S2 minus the edge also admits a KQR decomposition. So at a high level, this allows us to switch between using two overlapping cliques in a decomposition. In 2024, Delcourt, Kelly, and Postle showed that there exist KQR absorbers, which are built by sort of gluing boosters and hinges. Unfortunately, the rooted degeneracy is simply not sufficient for the minimum degree threshold that we're going for in our theorem. And it's the best minimum degree threshold known. So unfortunately, rooted degeneracy is just not going to cut it to embed these absorbers. Instead, we take some inspiration from the structure of these absorbers themselves. It turns out that implicitly in their construction, each gadget, each booster, and each hinge is partite. And by that, I mean in the rainbow sense. There's a couple ways to generalize partiteness to hypergraphs. And here we mean that sort of every edge hits each part at most once. So again, at a very, very high level, the boosters and hinges are a partite blow up of a clique. And in case you haven't seen it before, the T blow up of a graph is obtained by replacing each vertex X with an independent set of T copies of X, and sort of taking the complete graph between these new independent sets whenever you had an edge. Well, then the classical Erdős-Simonovitz theorem bounds the maximum number of edges in a graph that does not contain a blow-up of a complete bipartite graph. This feels like we're on to something here, right? Because if we can show then that our high minimum degree graph actually contains too many edges, well, then by the Erdős-Simonovitz theorem, we would contain sort of a partite graph. So at a high level, the dots are starting to connect. And also, Erdős and Simonovitz introduced the classical notion of supersaturation in Turán theory, which broadly says that if a graph H is above the Turán density of a graph F, then H not only contains one copy of F, but actually contains many copies. Well, this sounds like this is really the right track to go down, because we wanted to say that for each of our partite gadgets, we really wanted to say that there are many possible places that they exist in this graph. So can we use Turán theory then to show that G has high enough edge density to guarantee the existence of many copies of a KQR absorber? As a little bit of now we're going down a trek into hypergraph Turán theory. And so the Turán number, which we denote X and F, of an R graph F is the maximum number of edges in an F-free R graph on n vertices. And then the Turán density of F, denoted pi of F, is this limit of these Turán numbers. So Keevash generalized supersaturation to R graphs and showed that if an R graph G is above the Turán density of F, then it not only contains one copy of F, but many. Great. He also generalized a result of Rado about blowups to R graphs as well by showing that the Turán density of an R graph F is the same as the blowup of F. And finally, Spencer gave an upper bound on the Turán density of complete graphs. Now, this is not the best known upper bound. That's due to Duquesne, but it's only for large Q, it's only a factor of E off. And for purposes later in our proof, this one was just actually easier for us to use, and it suffices for our purposes. Okay, so then the idea is to show that this minimum degree of G means that G is above the Turán threshold of an appropriately chosen sized clique, and hence it's above the Turán density of a blowup of that clique. So then G contains many copies of this blowup, each of which contains the desired gadget. Bing, bing, boom. We have many possible places that the gadget exists in G. Use the embedding lemma. Prove that our omni-absorber exists in our setting. Skip off into the sunset. Unfortunately, this is not enough. The previous argument, Turán theory, right? It's about finding subgraphs in our graph. So the previous argument gives absolutely no control over where the gadget is in the graph. And furthermore, we need our absorbers to be rooted, right? If we're trying to find this absorber, we're trying to absorb a particular subgraph L. So that absorber has to live somewhere relative to L. It has to have edges that interact with the subgraph L. And even worse, the edges in the absorber, because we are in the hypergraph setting, they might contain different numbers of roots, right? So maybe one edge contains 2 roots, or maybe it contains r minus 1 roots. We just don't know. We could have all different numbers here. Now, the key idea to fix this is that finding a rooted gadget is the same as thinking in the non-uniform setting. So we're going to let G prime be the subgraph containing only the vertices that are sort of complete to all the roots. Like if we want to embed a absorber for a particular set of roots, we're only going to think about vertices that are complete to these roots. Then we're going to let A prime be the non-uniform hypergraph obtained by deleting all the roots from the gadget A we want to find. So, and as we talked about before, because each edge of A might have a different number of roots, what we get by deleting the roots is truly a non-uniform graph. And finally, then we note that a copy of A prime in G prime corresponds to a rooted copy of A in G. And that motivates us to develop a non-uniform Turán theory. Now, I'm definitely running low on time, so I'll just stick to sort of the first key definition here before I wrap up. But we develop the idea of a Turán space. So for a hypergraph G, we let G to the I denote the subhypergraph containing exactly the edges of uniform I and G. And a hypergraph G is R-bounded if every edge contains at most R vertices. So then the definition of a Turán space is that if F is an R-bounded hypergraph, we say that this vector of length R, alpha 1 through alpha R, is a Turán point of F if for every epsilon greater than 0 and every n big enough, the following holds. If G is a hypergraph on n vertices, such that in each uniformity, the edges of G satisfy that they're above this threshold given by the vector, then G contains a copy of F. So instead of just counting the number of edges as a whole, we're counting them in each individual uniformity. And the Turán space of F is the closure of the set of all Turán points of F. I think the last point that I want to wrap up on is Luke always says to me, when you find the correct definition, then everything will fall into place. And so I think that was really true for this project, is that as soon as we hit on this definition, um, it solved all of our problems. And there have been other people who've developed versions of non-uniform Turán theory. None of them worked in our setting. So our definition is certainly motivated by what we wanted to accomplish for this proof. But it's actually a really natural generalization of Turán theory to the non-uniform setting. So we're curious to see what else can be proved about these Turán spaces, sort of independent of how we used them. But skipping a little bit, we were then able to use this definition to generalize the key results of hypergraph Turán theory to our non-uniform Turán spaces. So we showed a non-uniform supersaturation, a non-uniform blowup, and then a non-uniform Spencer's. And with that, we were able to combine all those properties, show that each absorber has enough space to embed in the graph, which then, as we talked about, is sufficient to prove that these omni-absorbers do exist in our hypergraph Nash-Williams setting. Thank you so much. Here's a quick summary of everything I talked about today. I really appreciate your time. Let me know if you have any questions.
All right, thank you. Any questions?
Yeah, that was a wonderful talk. You covered a lot of ground. So Mike, and you did it very well. I especially like that how you started with the takeaway that if there's one thing you take away is that the Nash-Williams conjecture is very important. So that's really nice. My question is about the absorption method. I actually have three questions on it.
Oh, great.
And the first is it sounded like someone, did y'all come up with, or was it around before? It sounded like it was around before. In that case, who did it? And, what was the original context? And the
Yes.
second is really just an observation. It sounded very algorithmic to me. So have you maybe considered making a program out of it? And my third question is, you talked how it was like really a way of embedding something. Does it work for other things too? Other things where you might want to embed something? That's it. Thanks.
Oh my gosh, those are all great questions. Let's see if I can remember all of them. So, in terms of absorption, yes, you are absolutely right. This concept has been around um, for quite a while. Let me see if I can find that slide. One second. There we go. Yeah, the concept of absorption has been around for quite a while. I think at least since the early 2000s. Um, there's definitely a little bit of a debate about where the idea of absorption like strictly comes from, because it turns out that it's actually sort of implicit in many people's works, sort of before the formal notion of absorption uh, was defined, right? This idea of starting with something that's almost and then transforming it into something perfect, right, is quite natural. So it's easy to believe that that's sort of the underlying idea in many places. Now the group, you'll see some names here that come up quite a bit: Glock, Kühn, Lowe, Montgomery, and Osthus. Um, they and sort of subsets of that research group formalized a type of absorption method called iterative absorption. So in particular, I think it was 2016 proof of the existence conjecture uses that really formal absorption method. And then Michel Delcourt and Luke Postle formalized another absorption method called refined absorption just a couple years ago. So that's a little bit of history there. In terms of the algorithmic question, that's a good one. And I'll say that we haven't really thought about it. It's definitely a lot of the individual pieces are very probabilistic in flavor. And so it's a lot of, we argue that this exists. And so I'm not sure. Maybe it's possible to turn that into an algorithm. I'm sort of grateful to not be the one to have to do it, perhaps. And then what was your last question? I'm so sorry.
Oh, no, great answers. I'm enjoying hearing them. Embedding, it's about embedding. Can this be used for other embeddings too?
Yes, absolutely. So the general embedding lemma in particular is quite powerful. It gives some really natural conditions for what needs to happen if you want to find an embedding. And so I think that is absolutely could be used in many different contexts. I think what's also really cool about this framework that Luke and Michel developed is that each piece, it's almost like very modular, right? Each piece sort of feels like you could take it out of its context in this framework and apply it to a bunch of different problems. So yeah, absolutely.
Yeah, thank you. That was really good. It's definitely a technique that I want to look into. And you said that like when a technique becomes a technique, it's been used in a lot of places, and then like it eventually becomes a technique. I've noticed that too. So very great, good talk. I mean, I really enjoyed it. It was really great talk. Yeah.
Thank you so much.
Cool. Any other questions?
I just have a quick question about the disproof of the folklore generalization. Did that blow out of the water any chance of another generalization, or do you think there is like another meaningful in some way generalization to, greater than 3?
Yeah, that's a great question. Let me find it. Yeah, it's a great question. So in some sense, it's incredibly unsatisfying because this number q over q plus 1 was just so nice. It actually fit a lot of patterns that we were seeing, sort of especially with the threshold for first finding a subgraph from Turán theory, then the threshold of finding a factor from Heinel-Semeretti to this. It fit really nicely. And so at least in some sense, it's blown that pattern out of the water. But I would argue that it's actually still quite important to find or to make progress on the KQ and fractional KQ decomposition thresholds. It turns out that many decomposition problems are actually tied to these thresholds, so that these values actually affect the threshold for other problems beyond just a KQ decomposition. So I would argue that it's important to find another generalization. It's important to like dig towards the correct number, but we were not brave enough to actually posit what that number would be.
Fair enough. Thanks.
All right. Anything else? Okay. If not, let's thank the speaker again.
Thank you.
All right. Thank you very much. All right.
Looking
I'll stop the
forward to
recording
seeing
now.
you.